Hello everyone and welcome to Rebel Way. My name is Andrew Sutherland and today we're going to be creating this Star Wars inspired scene in Houdini using the RBD bullet solver and the pyro solver both at the SOP level. Rebel Way already has a 12-week course on destruction and it's a pretty intense course with all sorts of things that you could use to take this further, and we'll cover all kinds of very complicated RBD destruction type shots. But what I was trying to do here is create a scene relatively quickly that looks complex. And in order to do so, I've used the SOP level tools so we can get some destruction and some explosions relatively quickly. So that was my goal for this project, and I've created a tutorial on the workflow for destruction at the SOP level, and this was all rendered using Arnold. So I'll include the shaders and everything in the HIP file. So take a look at that. But everything is pretty much done as much as possible at the SOP level, including the shader. The shaders is created at SOP level, and I'm saving that out as a attribute on the explosion. And we can read that attribute in Arnold, and we get this really nice looking explosion that we see here. So yeah, without further ado, let's jump into Houdini. So jumping into Houdini, let's just create a box, jump inside, and let's change the size here. Leave this at 1. And make sure that this is always at the right spot. Let's paste this in here and divide this by 2. Cool. Okay, so now we've got some sort of wall type thing. So first we have a geometry. And then what we want to do is we want to make sure that this geometry is clean. So in this case, this geometry is watertight because we just used a box. But you know, sometimes you get a geometry and it looks something like this, and we have this big open hole at the back. So in that case, you want to make sure that you close all the holes. In this case, I'm just going to put down a polyfill. And make sure that that is closed. Sometimes you need to change it to triangles, or sometimes our VDB things and just convert it back to polygons. But in this case, we have a box, so that's going to work perfectly. And the next thing that we want to do is we want to fracture this. So let me actually just create a little null network just to illustrate the workflow. So we have our geometry first. Then we're going to clean the geometry. Then we fracture the geometry. Then we create a constraint network. Then we send it to the simulation. Then we cache our simulation as points, and we transfer our geometry to those points. So I just want to create this so we know where we're headed. And when I go over it, hopefully things will make a bit more sense. Yeah, so this is our workflow. Geometry, clean our geometry, fracture, constraint network, then the simulation, and then cache. So in this case, we have our geometry here, and then we want to make sure it's clean, and in this case, our geometry is clean, and then we want to fracture it. And there's a number of ways of fracturing. One thing we could do is we could say VDB from polygons, and we can say density, full interior. Let's lower this, so pressing D on our keyboard, we're going to change this to dark. And you can see now we have a volume representation of our geometry, and we can scatter points inside this. So the purpose of this creating this VDB is just so that we get points inside. If we don't have this, it's just going to scatter points on the outside, and we want points on the inside as well. So that's why we're using this VDB from polygons. And then what we could do is we could put down a Voronoi fracture, and this takes our geometry and this takes our points. Let's just lower our points for now, so we have something like that. And you can see that now our geometry has been divided up based on where those points are. So if we were to take a look at these points and then look at our geometry, we can see that this structure has now been divided up. And this is a basic Voronoi workflow. If we wanted to visualize those pieces with a color, we could just say, we could put down a color. Let's check to see if we have a name attribute. We do. So a color node. And we can say random by attribute, and we can feed in the name attribute here. And change it to primitives. And now we can see our pieces. We can also use an exploded view. And we can, use this to check out all our pieces. And let's take a look at, if you don't have this name attribute, you should get it from this Voronoi fracture. But if you don't, you could always put down an assemble, and this will create the name attribute for you. Now obviously this Voronoi fracture doesn't look very organic. It's quite uniform, and you will see this look in CG quite a lot. And what we want to do is we want to avoid this sort of Voronoi look, and Houdini has some great new tools. Before, you would have to create your own recursive fracturing setup, but what Houdini has given us now is this RBD fracture tool. What is it called? It is called fracture material. RBD material fracture. So this requires our geometry, and we tick this on and we immediately have something. And as you can see here, we have multi-layered fracturing, and this is what we call recursive fracturing. So for just to start, I'm going to turn off this second fracture, and let's just take a look at this. This is set to concrete, so we're going to get, it's going to fracture this like concrete. If we change it to glass, we're going to have a glass sort of look, wood and custom, but if we want concrete for now. And this under the hood is creating a VDB for us, and then it is scattering points inside. And if I come to primary here, you can see this fog over here is creating the VDB, and we have a noise in this fog. So this noise is going to create some high values of density and some low values. And if we were to scatter points, then where the density is higher, you're going to get more points. Where the density is lower, you're going to get less points. So as you can see, you could probably have a high density here and a low density there, and that's how we're going to get this. And if we change this, you can see our noise pattern is changing, and that is coming from this noise. And obviously we want to keep our points low, maybe something like 5 at first. because we're going to recursively fracture this. So we want a low number at first, and then we come over to our second fracture, and what you're going to notice is that these pieces are going to be fractured by, again, another 5 points. So yeah, so we have 5 points, and then we're going to throw 7 points at each one of those 5 pieces and fracture that again, and that's going to give us this recursive, more organic type of fracturing. And again, we have the noise the same values that we had before. So I'm just going to change this back to revert to defaults. Revert to defaults. Cool. So next up is that we have this chipping. And like this would suggest, is that when we chip this, the corners are going to be fractured. So if we take a look at that, we can now see we're getting some of this chipping effect on some of the corners. So that's what the chipping does. And then we got this for the constraints. So if we were to put down a null here, we can look at our constraint network. So this is doing a lot for us for free. And this is going to give us our high res geometry, and this is going to give us the low res geometry. And take a better look at this. We can also come to the detail here, and we can turn on this edge detail. As you can see, currently we've just got these straight lines, but if we put on edge detail, so if we come over to this edge detail, make sure that we're looking at the high res geometry, not the low res, and we turn on this edge detail, and we turn on interior detail, and we're going to get this this more organic sort of cracking here. So if we take a look at the exploded view, we can now see we've got this nice organic fracturing. And if we also turn on interior detail, we should get, you know, some details in the middle. And this fraction node works on Boolean, meaning it's kind of like taking a box like this, and if we were to take a cutting plane or a grid, we intersect the two geometries. Let's give this a lot more resolution, make the size something like 3 and 3 here. And we were to Boolean intersect this with that. Turn this to shatter. And now we get, you know, a cut like this. And what we're doing with the noise is, like, if we were to put down something like a mountain, we get something very similar to what we get with this interior detail and details doing, is we're noising up these planes. That's going to give us this organic look. So like I said before, this is our high res geometry, this is our constraints, and this is our low res or proxy geo. High res geo. And so what we want to do is we want to simulate with the low res using the constraints, and then we use this high res for rendering. So next we're going to talk about the constraints. And if we take a look at these constraints, we can see that there's points here and all these points are being connected. And so if we just, let's take a look at our pieces. This is our low res. I'm just going to put down an assemble. And I'm going to say pack primitives, and we're going to say display as centroid. So now you can see these are the centroids of each one of these pieces. Each one of these is the number of the piece. And if we were to take a look at our constraints, we can see that our constraints are going from the centroid of each piece and connecting them. So this piece is being connected to each piece that shares a side with it. So you can see these two share a side, so these are connected. This shares a side with this piece, so that is connected. This shares a side with that. And so that's how the constraints work, is it's connecting all the pieces to the centroid of all the pieces that, and the Houdini understands this based on the name attribute. So you can see we have a name on all the points. We have, each piece has a name, and that's on the constraints, and the same goes for our proxy geometry. We have pieces on the primitives here. So the geometry fractured pieces have a name, the centroid of that piece has the same name, and the constraint also is assigned to the corresponding piece via that name attribute. And that's how we get this relationship between all the pieces. Let's see if we can fracture this a bit more uniformly. Let's turn off this noise. Maybe keep this one on. Cool. So these are our pieces. Let's add a third one. Maybe we don't need that much. Oh, we've got 4. Something like this, that's cool. We're going to work with that. We got chipping on. Let's turn chipping off. Perfect. So we'll come back to the constraints, but from now we're going to take a look at some simulation. And we're going to put down a bullet solver. And what this is a DOP network that's just been wrapped up into this RBD bullet solver, which we can use at the SOP geometry. So if we were to right click this and say allow edit context, and we jump inside, we can see we've got a very big network here full of all sorts of nodes and stuff like that. And what side effects did is that they looked at the way people were doing a lot of their setups, and they made this tool with a whole lot of different things exposed for us to use. And that just means that we can now do some RBD sort of stuff at a SOP level, and we have a lot of the setups already built for us. So it is quite important, I think, to understand what is going on here. And like I said, we have a destruction workshop that will go over this a lot more in depth. I obviously can't show everything in a YouTube tutorial. The workshop is very dense, and it'll show you how to manage and make sure that you're running your RBD simulations as optimized as possible so you get the most out of the DOP network. But this is I really like this this SOP solver for what we're going to be doing today. And it requires our geometry and our constraints, proxy geometry. What we're going to do actually is we're just going to work with the proxy geometry for now, and we're going to actually just pipe that into this first one and our constraints into the second one. And if we take a look at this, let's transform our pieces up a bit. Let's put a transform here. Something like this. And let's take a look at our sim. We need a floor. And as you can see, we now have our first simulation. Cool. So we have something, and you can see that our constraints are working pretty well, too well in fact, and they are holding this geometry together. So first we're going to come up to this RBD bullet solver, and under constraints here, we can see that we've got a name here, and this name is glue. And if we come over to our network here, under the constraints, we have this reading in as glue, and we could change this name, but I'm just going to keep it as glue for now. And if we click play on our sim, we get this. As you can see, this is all being held together, but too much. So we actually want to break this. We want these pieces to fall apart. So I'm going to first lower the strength to something like 0.1. And we're going to need some breaking thresholds. And so what that means is, that we have this glue being held together. We want to make sure that we have some rules to break those constraints. So I'm going to tick on force, and I'm going to set this as a value of 1. So anything below a force of 1 is not going to break, and anything above a force of 1 is going to break. So we need to make sure that we hit that threshold, and as you can see, we now have this breaking apart like that. So what I want to do next is take a look at different constraint types, and the next one we're going to look at is the hard constraints. And in order for those constraints to work, we're going to take a look at the constraints here, and what we need to do is we need to scale these down to a point. So in order to do that, I'm going to put down a facet node, and we're going to tick on uniqueify the points, and then we're going to put down a primitive node, and we're going to use this to scale down these lines to points. So under the scale here, we can just do this, and now we have that down to a point. Cool. So then next we're going to come over here, and we're going to come to the constraints, and the constraints here, and under hard we can see we've got hard here, and we're going to set the rest length to 0. Like we scaled those points down to 0, so the rest length is now 0. So let's head over to our network here, and under breaking thresholds, we're going to make sure that we've got hard, and let's put on the angle, and let's put, just for, you know, let's put a high value just at first of something like 10. And let me see. So under this material fracture, let's set this to hard. And yeah, now we're getting the behavior that we wanted. You can see that we're getting, this is all staying together, and we're getting this like bendy effect like a mattress. And this is what we get from the hard constraint. If we come back to this and we set a lower angle of, say, like 0.5, let's try that. And we're going to get some braking. Let's lower this once again to 1. Point 0.25. Cool. So this is our hard constraint. That's looking pretty good. Cool, so because we're just working with this proxy geometry and not the high res, we're viewing this low res version here. So what we could do is we could set this up how it's intended, and that is putting the high res in there, the constraints in there, and the low res here. And now we can see our high detail, but better yet, we can put down a file cache. So this is the caching stage of our workflow, and we're just going to cache the points, simulation points. So let's save that, that's fine. Let's call this cache RBD points, and let's save this to disk quick. Cool. So if we take a look at this file cache, we can see we have the points, which are the centroid of all our pieces. And what we need to do is take a transform pieces, and we need our points and our high res geometry. And with that, we now have our points, our geometry following along those points. And the benefit of this is that we're just caching just points, so it's going to be quick to read from disk and quicker to cache, and we've got everything we need. So I'm just going to pause the video here, and I'm just going to quickly build up some bricks and some wall, and we're going to use some constraints to pin the wall to the bricks. And we're just going to make a bit more of an interesting geometry to do some destruction on. So I will see you in a bit. Okay, so I'm back, and I've just got a box here, and these are the size, and I've just transformed it a bit forward and a bit back, something like that. And then I've taken a box and I've made a little brick. And then using a copy SOP, I've just, copied this out like that, and done that with another brick, this time above this one, so that one, and then, offset like that. So when we copy it, we get a whole bunch of bricks like this, and then again, another copy node, and we're just transforming it up this way, and a color just to give it a brick-like color, and we're merging that with that. Let's just dive inside and you can take a look. Let's take a look at the right view. Cool. So those are our bricks. And if we were to fracture this like we did before, RBD fracture material, and let's just fracture the wall first. So ticking on, let's just turn this one off for first. Take a look at this. Cool. We've got 5 points, that's fine. And then let's enable this one. This will recursively fracture that. Let's put like 40 points. Let's maybe change this noise frequency. Let's maybe lower this to 20 and add a third one. So let's maybe come back. Let's add more points at the beginning here. So let's make this, let's disable this one. Let's add more points here, like 15.
And on the second one, let's put like 30. And let's increase this. Yeah, I think that's cool. And we need to give this a name. So this is called fracture. Let's call this wall. And because we're not going to fracture our bricks, we need to create something a bit more custom. So what we're going to do is we're going to put down a assemble node. And here we're going to create a name. And this name can be bricks. So this, I'm going to call this create name. We could pack them here too, but I like doing this in two separate nodes. So let's make a copy of this and call this pack bricks. And on this one, we just need to simply tick on pack bricks. So let's connect that here and then here. And now we have a name attribute. We have a name attribute here, and that's come down here too. And as you can see, we now have these as packed pieces. Cool. But we don't have a constraint for this. Obviously here, if we put down a null, we can check out our constraints that we got automatically from this RBD material fracture, and we need to create that ourselves. So from here, we're going to put down a connect adjacent pieces. Let's connect that here. Let's actually just do this assemble. And here we just click packed. So I need to connect this here. So I need to connect this here and change this to connect adjacent pieces or surface points like this. And let's turn up. Let's make this something like 200. Perfect. And you see how these constraints here, if we check here, it has a constraint name and a strength. We need these two attributes. So in order to get that, we can put down a RBD configure constraints properties. Yeah, this one. And we just need the constraints, so we can tick this on, and this is going to give us a strength here, and it's going to give us a name, and the name is going to be glue. So this is all we need. And now if we take a look here, we put down a null, this should match with this one. And if we come over to the geometry spreadsheet, we can see the constraint name is glue on here. And if we come over to this one, the constraint name is also glue. So these are a perfect match. Cool. So we now need to combine our constraints so that we can work with this. And so what we can do is we can put down an RBD pack. And it takes in the high res, the constraints, and the low res. And we have that for this in this case. So here's our high res, our constraints, and our proxy geometry. And then for our bricks, we're going to use the same geometry for our high res and our low res. And we're going to use these constraints here. So now we have, two single outputs. And that means that we can just merge these together and they should work as expected. So we can feed this into a RBD bullet solver, RBD bullet solver. But as you can see, we've got multiple inputs I should say. So what we need to do is we need an RBD unpack. I'm here, and we're going to take in our geometry, our constraints, and our proxy. And here we can enter in some collisions, and here is a guided sim. So I have created, so over here I've got an animated rubber toy, and he's just moving through this wall. And I've set a keyframe here and a keyframe there, and we might want to trail this and post compute velocity. And because this is going to be moving geometry, we can pipe this into our collisions, and because it's moving, we need to make sure that it's changed from to deforming. So this will just take in, animated geometry. And let's take a look at what this gives us. We need to add a ground plane. And everything is just falling apart. So what we need to do is we need to put some boxes here and enable, make this part active and these parts inactive. So what we need to do that, we need to put down an RBD configure, and we can merge that in here. And you can see here that we have a static bound input. So I'm just going to bring this down. I'm going to change my perspective to front view, and here we can put down a box. And let's make sure that our box is there, and we need a box for the other side. We can just merge these together. Fit that in there. Let's just take a look at the top view. Cool. And then under the RBD configure, we need to enable this active, use bounds, and we're going to set this to 0. So now if we run our sim, let's change this. And I think everything should be correct. I think this is not breaking because maybe our constraints are too strong, maybe. Cool. So let's just set this to back to 1, and on our constraint properties, let's change this to 1000. let's modify our constraints over here by setting this to 1000. Let's try that again. Cool. Let's try this as 100. Perfect.
So another thing that we might want to do is create a constraint between these bricks and the walls. So all we need to do is take a merge and let's take this high res. We've already got this merge here, so that's the bricks and the let's take it from here. Let's take the high res here, and then we're just going to copy this constraint network. It comes from points. Search radius is 0.1, 100, 90. And it's just a little bit difficult to see because they're just points, but if we click on this points, we can see that we actually do have constraints here. So that's cool. We're going to put down this constraint network, constraint properties, and let's lower this, halve it by, let's make it 500, even let's try 100. And because we just need the constraints here, we can actually just merge them in with the constraints here. So let's put a merge down here. Let's make this a little bit easier by putting a null here. A null here. This is our high res. This is our proxy. And let's put a merge here. Let's call this brick and wall constraints. It's not making a big difference because our sim was looking quite nice from the get-go, but this is going to just hold everything a bit more together. And if we were to have bigger clusters of parts, you know, if this wall was bigger and you know, a whole section breaks apart, then the wall and the bricks are not going to separate. So that is going to make a difference for us. Just in this example, it doesn't look too obvious. Yes, I've just made a few tweaks and I've disconnected these boxes, and you can see how we're getting this separation over here. But if I add our constraints back in and we glue all these pieces together, you can see the difference here. So let's just run the sim quick. And this is what we wanted to see. We want to see the wall and the bricks all being held together. So now that we can see that that is working correctly, let's plug in our active and inactive regions. And now we know that it's working correctly. Perfect. Cool. Okay, so now let's try something slightly different. Let's disconnect our constraints here. And let's disconnect our constraints here. And then where we've got our bricks and our wall, let's come back over to this connect adjacent pieces. And let's change this to surface points. 0.5, 0.8. Yeah, that's fine. Let's disable this. Cool. So this is now going to hold everything together. And then under our constraints here, let's set this to hard. Let's set our force to 1. Actually, we're going to set this to 0 because we're going to scale this down. Then what we need to do is we need to scale these lines down to a point because the hard constraint needs points. So we're going to put down a facet node. We're going to take on uniqueify points and then primitive node to scale those down. So click on do transformations and scale this down to points. Just make this 0, 0, 0. And you can see we've got our points there. And then let's put that into our RBD configure here because we're not using the constraints from here. And then under the constraints on our bullet solver, we're going to come down to hard. And the name is obviously hard, and our rest length, because we scaled it down, is 0. And let's just take a look at what we get now. Cool. So these pieces are all sort of being held together and we're getting this stretchy effect. And that is, believe it or not, what we want. And we can then set up some breaking thresholds that will delete these constraints or change the name of these constraints to broken, and they'll essentially, the pieces will fall apart freely. But we want to have this sort of stretching part here, and it kind of feels like the wall has some sort of internal structure, like even as like there's some sort of metallic bars holding things up, and you see this behavior with walls breaking. So let's just take a look at the constraints and set up some thresholds so we can break these constraints once they reach a certain distance or an angle, or certain rules are met, and then these constraints will be broken and they will fly apart, and we'll get a very nice natural looking fracture and simulation. So we come up to here, breaking thresholds, and let's take on angular threshold, and let's set a value of 0.2. Let's take a look. Awesome. And I love how these pieces are coming apart, but all the bricks and everything are stuck together, and we're getting these large chunks and small chunks and a whole bunch of variety that we see here. So let's lower this constraint quickly and see what happens. Cool, nice. And if we want this wall to feel a bit softer or a bit more bendy, we can come back up to our constraints here and let's set this to 1. Let's see what we get with that. Let's set this back to, set it to 1 and let's maybe increase our threshold. Yeah, 0.1 I think is good. So I'm quite happy with this simulation, the way it's looking, but if we wanted to, we could also add some more constraints. So we could take a copy of this and so let's make a copy here. We could do something like that, and we could instead of having hard constraint, we could set this to soft or glue. Let's set the strength to 1, and then let's merge this into our constraints here. Okay, let's go back up here. Let's increase the strength to 10. Set it to 100. Cool, so I've just made a few tweaks. I've got this, I've got our constraints for all the pieces here, and I've set that strength to 100. It's set to glue, and then on our main RBD bullet solver, we're just using the hard constraints to break this angle here. And we have, these are our values, strengths 1, so on and so forth. And obviously you guys can play with these settings and do your own experiments, but this is the basic workflow for the destruction that I used on the Star Wars scene. Let's just take a quick look at caching so we can cache our points. We need to cache simulation points here. Let's cache this to disk. So here we have our simulation points, and we need our objects. Let's call this out wall and bricks. Let's put down an object merge. There we go. So we need to take the bricks from here and our high-res geometry from there, merge that in, and now we have our sim. Cool. Next up, we'll dive into the overview of the Star Wars project, and we'll basically use this setup. So hopefully with this out the way, you'll know how to build your own destruction effects, and you can see how I've used the setup in the Star Wars scene. Cool. See you in a bit. Okay, so welcome back, and we're going to dive inside the final project that you see here. And most of the good stuff is happening inside this sim RBD, but I've also just put down Tommy. I always like to add a little Tommy into my scene so I can make sure that my scale is correct. I think just visually having an idea of the size of a person versus your building or character really helps with making sure that you've got your scale correct. So first things first is that we're reading in this geometry, and it's just a static geometry. If you had some animated geometry, you could always just put down a time shift and freeze it on the frame. So this is, in this case, we're reading in frame 2 because we're on frame 2, and you just delete that, and now it's going to stay on frame 2. So if this character was walking, you could have him walk for a few frames, and then in the reference I looked like in the reference I saw, he was walking, and then it looked like he just time shift, and the explosion took place on the frame that he was frozen, and then the sim takes over. So if you want to use animated geometry, that's how I would do it for something like this. But in this case, we've got the static geometry, and we need to fracture this. So I'm using the Voronoi fracture in this case because the destruction is predominantly going to be covered up by smoke, and I just wanted some pieces to fly out so that we could trail and get nice trails with our smoke. So I ended up just using Voronoi as this is the most efficient, but I'm sure you guys will all be comfortable now swapping this out for the RBD material fracture and get some more details on your simulation. But in order to fracture this, I used a point, and the point is at the origin of my scene. Let's enable this so you can see that a bit better. You can see there's our point, and I'm transforming that up there, so it's now close to where we want our sort of fracture to take place.
And then what I'm doing is I'm using a point replicate to replicate those points a number of times, 108 times. And we've got, something like this. Doing that again, this time in a tighter ball. And this one, same thing, except we've changed the scale to 0 here. So it was like that. And then, so now it's just, a bit more flat. And then I'm transforming this out a bit, merging that all together. And then I'm using this ray top to ray these points onto our 8080. So under ray set to minimum distance, and these points are now going to stick to our geometry. Same thing for this side, except we're transforming the points out here and then raying them back. So now, if we take a look at that, all our points are sticking to our character. Just going to change this to dark quickly. Hit D on my keyboard. You can change that to dark. And here I'm grouping these points and I'm giving them a name, input points. Like that. And we don't really need this merge, but we're now feeding this into our Voronoi fracture. Cool, so we now have this fractured, and I've saved that to disk. Save that again. And here you can see I'm putting down an assemble node to create a name attribute, and then coloring the pieces. Cool. Cool, so now we can see all our pieces. If we put down an exploded view, these are all our pieces. Cool. So from there, we're going to make a constraint network just using the connect-adjacent pieces. And then we're going to put down an RBD restraint properties. This is set to soft, glue, and these are our strengths. Then we have an RBD figure. Then we have an RBD configure that's reading in our constraints here and our fractured pieces into the high res. And the one thing I didn't show earlier is that we can actually create a volume. So if we come up here, we've got a point and we've got a switch, and we've set this to $f == 2. So this is only going to show up on the second frame. You see that it flashes on and off. So let's just go to the second frame in order to take a look at this. And then we time shift this +1. So by time shifting this, we now got it to work on the second frame and the third frame. If we merge that in, so you'll see it's just on for 2 frames now. And then what we're doing is we're using a point replicate, and this is our size, and it's set to sphere. If it's a box, they're going to change into the shape of a box, but we want sphere. And then we've got a wrangle, and we're just giving all these points an ID attribute, and the ID attribute is based on the point number. So if these all have point numbers, and we're saving them to the ID. Then what we can do is we can transform them up and out, and I've got this expression on my pivot, and this just means that when we scale things up, it's going to scale from the origin of the object, not from the origin of the scene. If you've got something at the origin and you just put a transform, it'll transform up nicely. But if you've got something away from the origin and you try and scale it up, then you're going to get a bit of a problem. So using this expression just means that it changes the world space origin to the center of your thing. So if you do this,
it scales up around your object, where as if we have a normal transform, and we try and scale this up, see how it moves out of the scene. This is super annoying. So you just come over to the pivot, and I've actually even saved this as a preset, center pivot transform, and now it gives me this expression here and it scales it up nicely. So that's what I'm doing with this transform. And then I'm just using this attribute noise vector to mess with the position a bit using my settings, and I'm merging that in. So we've got our first points and then a copy out here, and because they have an ID and they have the same ID, we can then put down an add node and say group by ID, and we're going to get these lines. And then once again, I'm just transforming these. These are my settings, and I wanted to make sure that it intersects with my character here. So we've got this is going to be some velocity, and it's going to shoot out through my character. So if I come back here, and here we're resampling, so you can see before we only had a few points. Now we resample, we have a whole bunch of points on here, and we've also ticked on compute curve view, so we've got this curve view attribute. From there we're putting down this polyframe, and we're saving the tangent as V. So if we take a look at that, we should have so if we take a look at that, we have some velocities along our tangent, and here we're noising up the velocities, so you can see how these are all sort of, our velocities are everywhere. And then using this wrangle, I'm just fixing the direction of the velocities, and I'm scaling it up by quite a lot. So let's take a look at that. Cool. So that's what we're getting from our velocity. And here we're setting the curve view to our P scale. So we have a value on these lines, which is a curve view, and it goes from 0 to 1. So maybe just to illustrate that, we can put down a color, and we could say ramp from attributes, and we could say curve view. And you can see now we set this to red and this to blue. So these have a value of 1 and these have a value of 0, and we can use this information to drive the P scale. So we're going to copy, like, all these points are going to be, we want them to be bigger here and smaller over there. So we're just going to manipulate that with this. We're inverting this because you can see this is a value of 1 and this is a value of 0, and we actually want to flip that. So we're saying 1 minus curve view, and then we don't want it to go completely to 0, so we're just adding 0.1 over here. And once we VDB that, we get this, and we're battling to see it properly because we've got a whole bunch of different fields layered up on each other. So in order to hide everything and only look at the density, we're putting down this visibility node, and now you can see that we've got these spikes. Maybe a better way to show that is just by saying, let's say, copy the points, and we put down a sphere here. let's just take on pack an instance. Yeah, so you can see that this is inheriting the P scale. So if I were to resample this and I want to reduce the number of points. Yeah, so you can see that all this is a bunch of points along these lines, and each point has a P scale, and that P scale is being multiplied by that curve U. So over here, they're going to be 0, and then we added 0.1 here, so they don't have the values don't go to completely to 0. Each point is still going to appear somewhat, but the lowest value is going to be 0.1. And over here, this is a value of 1, and this is a value of 0.1. And we're just converting those to VDB. We're making it density, and we're hiding the velocity. So now we've got this volume representation of our force. And we're going to put down a null, and we're just going to say out velocity force, and we're going to use this to delete our constraints. So not only when this explosion appears, because it's just for a couple frames, so when this appears, it's going to delete the constraints completely, and it's going to also push out the pieces where it intersects. So it's going to delete the constraints completely where this appears, and it's also going to push those pieces out. So if we come back to our RBD solver, and we come down to constraints, you can see here we've got this use vex expression, and we're saying here, check where this volume sample is and delete anything with a density above 0.01. And you're probably wondering, where do we read this in? And in order to see that, I've put a note here so we can remember, we have to double click. And then I've got a pop-up vec by volumes here, and this is where we're reading in that null. So this comes from here, and we're using that vex expression where is it? It is here. We're using this vex expression to delete our constraints. So we can take a look at our constraints here. And as you can see, they have been deleted in the center where that spike, where our force is coming from. Where on frame 1, we've got all our constraints. So you can see that, and then when it appears, boom, those constraints are now deleted. Then over here, I also added this sphere that's just being animated along here, because I wanted something to physically push over this character. So this is also switches just here so that it just appears for a little bit and then it disappears, because I didn't want it to pop out the other side. I just wanted it to be like, to topple this character over. You could have just got this possibly from just the forces alone, but in order to get this done quickly, I just added this little sphere, push it over, and we've got the effect that we wanted. So coming back here, we've got a braking angle of 0.2. We're reading in the constraints here. These are all my settings. We've gone over all this stuff. So just check out what the settings are. These are our iterations. We've got gravity. And that's it for our bullet solver. Let me just check if I'm missing anything. I wasn't using this, so you can just ignore this.
This is for our explosions. Cool, yeah. We've got our transform pieces and we're reading in our geometry from here. So like we did before, we're caching our points to disk. So let's just run a quick flip book. Cool, so this is the result, and this is what I was kind of looking for. I just wanted this character to fall over, feel like he's being impacted by, you know, the explosion, and some pieces that fly out that we can trail for our pyro simulation. Cool, so what we're going to do next is we're just going to put a null doubt here for our RBD, and we want to create some collision geometry out of this. So we're going to create a VDB out of this, and it doesn't have to be high res. We just, you know, something low res that's going to move through our smoke simulation. And I'm saving this out as an SDF field. So on our geometry, it's surface, and this is being saved to disk. And we're putting a null as out SDF. And then on this version, you know, save this to disk. I'm just going to disable this because I haven't saved it yet. And I've got our geometry version. Cool. So this is our geometry, which is going to be used for the collision. So it doesn't, like I said, it doesn't have to be high res. And we cache that out to disk and put a null out for reading it into our sim. Cool. So the other thing, before we start working on our pyro simulation, is we want to add some more details to our RBD. So this is our sim. And what we can do is we can give this more detail by creating some debris. So using this debris source, and if you guys want to work on that wall idea, you can just add this to your setup. So what this node is going to do is it's going to look at our fractures and the parts that are moving very quickly, and then it's going to scatter points on those areas. So we're going to save that to disk. And we also have this age attribute here. So we can put down a color node and we can read in this range. And we can just see the points that are newly birthed are going to be white. And as they get older, they're going to go black. And I just made this quite a tight ramp because I just want to use it just when things break apart. We want to emit debris. So I've made a color based on the age here. And then we're putting down a blast and we're deleting anything that is dark. So any dark colors are going to be deleted and the white is going to be kept. And you can see that here. So now if we take a look at this, these are just the areas that that we use, and this is quite easy to manipulate. So you can mess around with these values until you get what you want. Then I'm just putting down a delete. And I delete by group because I didn't want the debris to be everywhere. I just wanted it to be in the main sort of section here. And I'm just animating this box really. So this is what I had. So really the main part of the debris is just these first few frames. And the main reason I was doing this is just to speed things up. So if you're going to be doing something different, probably remove this and, you know, delete your debris where you need it. I think while I was setting it up, I didn't have this, and I ran the sim and I looked back at it and, you know, there was too much debris. So that's why I added this. And here again, still too many points, so I've put some vex here, and I can use this expression to delete points, or I often use this for water simulations. So if I'm running a high resolution simulation and I want to run a flipbook relatively quickly, I use this reduce points for display, and I just reduce my number of points, and I can get a faster feedback. And I was just doing that here so that I would, could control the amount of debris that I would get. And here you can see my debris is being cached. And that is what I used. Here I'm just deleting all the attributes I don't need, just some cleanup really. Here I'm setting a p-scale and I'm randomizing it a bit. And in order to see that, I'm using this copy to points. And instead of a sphere, I just put this, which is a bit more sort of organic looking. You could probably get away with the sphere, with the motion blur, you probably won't see it, but I often like doing this for debris. And that's it for the out debris. Let's run a flipbook quick and take a look at what we've got. Cool, so this is our debris simulation, and you can see it's inheriting the velocity of the pieces and it's colliding with our geometry. So pretty straightforward. The DOP simulation is here. We're reading in our out SDF into the second input for the collisions, and our points into the first input, and it's literally just a pop simulation. So for pop simulation, we have our ground, obviously, some gravity, our pop object, our pop solver. This is what you get in just a normal pop sim. And the only thing I'm really adding is some wind resistance, and this for our collision. So for my collisions, I'm basically using this pop VOP here, and this is a bit more advanced. This is the sort of thing that you see in our Mastering Destruction workshop, and this is it's a lot more efficient than just feeding in a standard collision with an SDF and a volume. Basically, what this is going to do is it's going to look at our character, and we're gonna create a VDB version of that. And what we're saying is we're saying, okay, we have a bunch of points from our pop simulation. Check which points are inside our character, and if they are inside our character, then we need to see how far we need to push them to the surface. And then we're basically pushing those points to the surface. So let me do that out here. So here's our points. Here's our SDF. And I'm just gonna time shift this. And let's delete that just so that it's no longer moving. And then we're gonna make a bound. Whoa. Let's just make a manual bound, because we've got pieces that are flying very far away. That bound is not working properly. So let's just make a box here. Cool. That should be fine. And let's go VDB from polygons. Convert this into a density. And then let's scatter. Cool. So we've got an SDF field and we have a bunch of points. So now I'm going to put down a point VOP. So we're going to connect the points to our first input. and our SDF to the second. So the first thing that we're going to do is we need to find if the point is inside of our character. So we're going to use a volume sample, and then under this we're going to say the input is the second input, and we're going to use the name. And if we come to our SDF, we can see the name is surface. So under name we can just put surface. And the sample position is the point position. And so this position is the point position, and then let's plug this into the color. And it's a bit difficult to see, so let's maybe increase our number of points. And you can start to see there that we've got our geometry. We can see the 8080 in there. Maybe let's change this to, yeah, this is fine. Let's make our box a bit smaller. Whoop. Make our box a bit smaller. We might be able to see a bit better there. Cool. So we can see our character inside here. Let's lower these points. No. Cool, something like that. So if we take a look at our geometry spreadsheet, we can see our color information. And at first we have 0.63. And if we come down here, we start getting negative values. And this is basically how far the point is inside of our geometry. So we can use this. So what we can do next is that we can put down a compare node. And then we can feed this into a two-way switch. And we can set this to less than 0. So if this is less than 0, then we're going to have something. And if it's more than 0, we're going to have something else. So let's put down a constant. A constant. And let's change this to vector. So now we have 3 values, and we can make this a color. So R, G, and B, let's make this 1. So this will be red. This one we can make blue. That. And we can feed that in there. And this one in there. So red is going to be, inside, and blue is going to be outside. So next what we're going to do is we're going to put down a volume sample gradient, or volume gradient. And this node, so basically our character here, this 8080, we have this as an SDF field, assigned distance field, and we want to find out where the ISO, so the ISO surface is a value of 0, and what we can do is we can use this to look at the values of the ISO surface. So if it's right on the edge, it'll be a value of 0, and if it goes in deeper, we'll have a value for that. So what we want to do is we want to feed in the position of the gradient, you can think of this like the normals of a volume, and we're going to say it's the second input. That's where it's coming from. And the name is surface. And so if we take this and we feed this into the color, you can see like we've got basically the normals of our volume. That's basically what it's doing. It's like you would compute normals on your geometry. This is computing the normals on our volume. And if we were to take this normal information and put it into the normal, and then we look at our display normals, we can see that these points now have a direction. And we're going to normalize this, so we make sure that all these, all our normals have a value of 1. So this information is the direction. This is how, where it needs to go, and how far it needs to go is going to come from this surface field here. So what we need to do is we need to add the current position of the points plus the normal, and we're either going to push them or keep the normal position. So this second one. And then we can plug this into our position here. And you can see that it has pushed these points out a bit. It's not quite perfect yet, but it's pushed them along that direction. So let's just make a copy of this and put the colors in again. And plug this in so we can still see where our problem areas are. So the red is still inside the volume. Okay, so it's not quite right yet, and in order to fix that, we first need to negate these the normals, because these points are telling us how far inside they are, and we don't need to just add this to here, but we actually need to multiply. So we need to multiply this position and multiply that with the normals, and then we're going to add this amount, and that should have pushed our points actually inwards. And what we need to do is we need to negate the normal here in order to fix that. So negate just like inverts the values. And I think that should be correct. Let's come back out here. Let's put down a blast. So let's delete at cd dot x greater than points. Cool. Yeah, so it is now pushed all the points to the surface. Let's add some more points. Excellent. So this is working. Cool. So if we use this setup inside our simulation, on each frame, it's going to check the position of our particles and it's going to push it to the ISO surface here. And that's what I've done in our pop simulation. So this is the exact same thing. So here we're computing the gradients. Here we're normalizing them. We're negating those values. We're multiplying it by this this volume sample, so the position of how, where are the points inside that volume. We're using the compare to check if they are inside. If they are, then we're going to multiply this value with this. So where they are inside the volume, where they need to go, and how much. And then, like we said, this is just for visualization of the color. And then we're pushing that out, and that's it for that. So when we run the sim, we get perfect collisions. And this, although it can be a little bit more complicated to wrap your head around, it's far more efficient than actually calculating this in any other way. And like I said, the destruction workshop is really brilliant for stuff like this, because you can manage gigantic amounts of particles, gigantic amounts of debris and destruction, and getting perfect collisions every time. Cool, so here's the result for our debris. And another thing to mention is because we've ticked on stick-on collisions, and we're not actually using this character as a typical collision. So it's not, these particles aren't being stuck to the character, it's only being stuck to the floor. And we're only going to get that by doing our custom collision the way that we did in that VOP. That way, it's not going to stick to our character, but it is going to stick on the floor. Cool. Next up, we'll take a look at some smoke simulations. So moving on to our smoke simulations, we're going to take a look. Let's actually take a look at some of the initial explosion forces. So here we've just got a point at the origin, and I'm transforming that up so that it intersects with our character. So our character is here, and then I'm just adding a pyro burst. So I worked on this at the origin, and if we take a look here, you can just see a spike, but I'm using it, I'm copying then this explosion, this pyro burst, to that point. So up here, so we just have something like that, and then again transforming this. Just I was changing, what did I do? I changed just the position a bit from there, just more center. Then I'm minusing 2 frames, so I'm basically making a copy of this, but it's offset by 2 frames, and transforming that to the front. So basically we're going to have a blast here, then 2 seconds later we're going to have a blast here, and we're merging that together. And let's just take a look at the settings for the pyro burst. So these are the settings that I used, and yeah, you can use this to like change the size, the spread, the roundness, all these sort of things, number of trails. But yeah, that was the settings I used. Let's go back, and I put a null here so we can reference that if we need. And here I'm converting to VDB, and I'm saving the velocity as vel, and we're creating a density, then a visibility just so that we can view just the density. So we have something like this. So blast and a blast. Let's take a look at these trails. I'll come back to this because we're going to feed this all into a pyro simulation. But first, let's take a look at the trails. So here we have our points. This is the points from our RBD sim. And here I'm taking the original geometry. It's just static. I'm scattering points on this, and so we can come over here. See, this is the number of points, but under the attributes, we're also transferring the name attribute, because we need to have the name attribute to transform these pieces with the sim. And if we can transfer that name attribute onto points, well, then these points are going to move with our simulation. So we can have just points moving. So that's pretty cool. Here we're creating an ID like we did before. So each point has a point number, and we're just going to store that as the ID attribute. We're using our transform pieces, using the name attribute. And then here we're going to compute the length of the velocity. So we can visualize that by putting down, we're going to visualize it by entering this into the color. So now the fast moving parts are going to have a value of 1, and the slow moving parts are going to be black. So yeah, we're just using this fit here. and we're clamping it a bit, 5 to 25, and that's going out to color. Then what we want to do is we just want to delete the dark parts using this expression. So now we only have the fast moving parts, and I didn't want to include this part, so I just put down a box. I deleted everything that was behind the character because I wanted to keep my domain fairly small. And then I'm using this bound to just keep these parts. So I'm keeping this. If I were to change this to delete selected, we'd have everything else. So essentially this is my domain, what we see here. This is the only part that I want to sim. Then I'm trailing these. And I'm going to connect these with a line based on the ID. I'm going to resample that and compute the curve view. Then like we did before, basically I'm just importing the curve view, fitting that and putting that to color for visualization. But the main thing that we're doing is we're exporting this as p-scale and density. So if we take a look at that, we can see this is a high value and then it trails off. And if we are to copy points, so let's actually just take a look at that. Copy the points. Stick on pack an instance. And a sphere. We can make this smaller. We can see that this now like sort of trails off, and so this leading edge is going to be higher value, so this is going to be more dense and this is going to be less dense. So when we convert this to volume, we'll see it sort of fade off. And here we're creating a temperature, and we're just using the very front parts as the temperature. I think in my render I actually even masked this out. So if you want, you could just like, not do a temperature over here, or just, compensate for it in comp. But essentially we're going to have some fire at this leading edge. And that's just by taking the curve view, a fit range, and exporting that as temperature. And this ramp is like, you have to come back out here, but we can see how much temperature we want. So if you want the whole thing to be on fire, you do something like that. But I wanted just the very tips. Yeah, so we're setting the velocity to -1. And so here I'm setting velocity and I'm making it -1 because I want the velocity to actually push the smoke in this direction backwards. I don't want smoke to push forwards and overtake the debris. So that's why it's negated in going backwards. And if we were to visualize this, I'm just rasterizing the attributes. So something like that. And I just cache that to disk. Oh, we're rasterizing the density, the temperature, and the velocity, and these are our settings. We cache that to disk. And then I'm just using this wrangle to manipulate the data a bit more. So I'm lowering the velocity, I'm lowering the temperature, and I'm lowering the density. And that was just based on what I was getting from the simulation, and I needed to tone things down a bit, so I just did it in a wrangle rather than going back and changing things and caching it out here. The next thing I did is I added this volume fog, and this is just going to give us some breakups in our density, so it's not so uniform. If we want to take a look at our trails, you can see the temperature now. And I'm not going to change this now because this is how I did the simulation, but after I did a render, I didn't like the temperature being in these trails. So when I was a nuke, I just basically masked out the temperature parts. So it just got smoke trails. But you know, I'm gonna keep it in here because I think it's good. You know, if you're doing it as something different, you might want to have these trails to be on fire. So you can see how that's done. Then I'm just saving this as out trails. And then this is going to be our main explosion. So next up, we're going to take a look at our explosion. And this is the setup. It's quite simple, but I feel quite effective. And like I used the RBD bullet solver at the SOP level, we're doing the same but with this pyro solver. So these are quite new tools in Houdini, and the intention of side effects is to have these solvers at the SOP level, because you can buy a cheaper license basically. So studios can hire artists, and they can have a cheaper license, and the leads can have the full license with, you know, the DOP network. And I do think it is pretty important to understand these DOP networks, and I think you learn a lot by really engaging with DOP networks. But this makes things a whole lot simpler, and I think we've got a really good looking explosion out of quite a surprising simple setup. So if we come over to the network, the most important thing, of course, is your emitter, so your source. And I've just got a point here. So this add node is just set to creating a point at the origin, and then I'm transforming it up, and I'm, you know, the reason it's been transformed up is that I want it where our character is. So if we come back here, you can see we then copying this pyro burst to that point. And if we come to an earlier frame, we can see here's our pyro burst, and if we have that transformed into place, we have it intersecting with our character. If we come over to the settings, so we have this scale along trailing. I always make sure that this is ticked on, and we're sourcing some density, and it looks like we just got density, temperature, and burn. So if we come over here, these are our settings, and of course you can play with the spread angle, you can, you know, mess with your shape. But this was the shape I ended up landing on, and I just changed the shape. I ran a few wedges, so I had an initial explosion. I set up some collisions for it. I ran a test. I didn't quite like the shape I was getting, so I came back, tweaked it, just made a few changes until I got something that I was happy with. So I'm just transforming this further in. I probably did this after my initial explosion, probably just moved it in. And again. So not only would I change my settings here, but I would also change the scale to get the end result that I was looking for. So that's what those transforms are doing and where they come from. Same thing goes again, another pyro burst. And a lot of these techniques and setups have been done in our previous tutorials on YouTube, so you can go back, check out the Fire Monster one, and I think Urban did a few with some explosions. So go and check those tutorials out if you want more information on doing fire and explosions. But I'll cover what I've done in this scene here. Again, just transforming this into place, time shifting, so, you know, this is delayed. Before it was there, now it's time shifted 3 frames later, and a third one. Exactly the same process, just merging all three of these in together. I'll show you the settings on this. All the same. This one. Let's see. All the same. And these just get merged all together. So now we have a blast, blast, and a blast. And I was sort of imagining, you know, we have like some sort of laser beam hitting here. So you have an explosion here, then an explosion out the side, and maybe one in the middle. So boom, boom. And let's maybe just do a quick flip book. Yeah, so that is my timing for my explosions. And then all our attributes are on points here. So we've got burn, density, and temperature, velocity. Those are our most important ones. And I'm then rasterizing density, temperature, burn, and velocity. So basically converting these into VDB. So we now have this as voxels, voxel information. And so we can send that to the DOP. Here, I'm also merging in our trails. So I have a trails, and this one's a bit long. We could delete this if we wanted. I'd probably go back and delete that. And here I have a surface field for our collisions. So the collisions goes in here, and our source goes in the first input. So this is coming from out Collider SDF, which is here. Cool. So we're reading that in for our collisions, and we literally just saving that out to disk. So let's take a look at our settings. So I was using the max size to limit the size of my explosion, because obviously the bigger your domain, the slower your simulation is going to be. So let's just take a look at that here. As you can see, I came in through my camera. And I adjusted my domain accordingly. I probably should have made this extended this, so I'll probably run this again and make my bound a bit bigger. So let's take a look at that. So here, extend that out. Cool. So then cache that out to disk again. And so this is our voxel size. I was running tests at 0.1, and then for my final resolution, I just multiplied this by 0.5 to have a higher resolution. Padding. And our density is going into density 0.2, our temperature into temperature at 1, and our burn is going into the flame at 0.1, and V interval at 1. We've got a bit of dissipation here. And under shape, we've got our buoyancy, some disturbance. and this disturbance is animated. So in here we have a value of 6. And actually, looks like I've kept this at 6. I do usually animate this. So at the start I usually have a higher value and then I trail this down, but it looks like in this case I didn't do that. I just kept it at 6. Turbulence. And if you take a look at the fire tutorial I did last time, I go over these settings a bit more in detail. You know, I ran a few examples of what this exactly looks like. I'll actually just show that again here quickly. So this is from the fire tutorial, and you can see here this is disturbance. This is what the result of disturbance is doing. This is shred, turbulence with a scale of 10, turbulence with a scale of 4, shred with a scale of 5, and this is unmodified. And I love doing these sort of tests so I can just see exactly what a microsolver is doing. So this is one is unmodified. This one is, you know, got some turbulence with a lower value. And I urge you guys to just run tests like this and compare. So in this case, we've got turbulence, which is, this is what turbulence looks like. It just takes your initial simulation, and you can see that these are almost like velocities, and it pushes your simulation around. And in this case, this is a low value, so we're not seeing a huge result in this one. This is turbulence with a scale of 10, and here you can see a bigger difference. We're getting some more swirly motion here. Disturbance sort of moves each voxel around, and you get more of this sort of puffy, smoky look. And I often use this to sort of try and convey scale a bit more. You can see how this one almost to me feels like it's smaller in scale, and this one feels larger. And a lot of that illusion comes from this sort of puffy smoke. And this also gives great surface detail on your explosions. You can't really see it here, but in our explosion here, this, what you see here, this sort of detail is very much coming from the disturbance. And so if we double click on our pyrosolver, we can actually add some more microsolvers like you do in DOPS. And so here I'm putting down another gas turbulence. And this time you can see I am in fact animating. I almost always animate these with explosions. So you can see that we're starting on frame 20. We've got a value of 2. And then on frame 25, I bring this down to 0. So we've just got some swirls initially as the explosion goes off. It goes boom, and then we have those swirls. And on this one, this is just adding some more gas turbulence. This one's on all the time, and it's just a light touch of turbulence. And then I always add a gas vortex confinement, and this is just going to accentuate or exaggerate the motion in your simulation. So this is going to, so if you've got swirls in your simulation, this is going to just exaggerate those a bit. Yeah, so I've just got a light touch of confinement, and that goes out into the forces. So it's actually a pretty setup. SideFX has done a lot of the work for us by creating this tool, and I cache that out to disk. And then the next thing that I do is I put down a pyro look. This is basically like shading your simulation at the SOP level. And what's great is that you can bake this out to a shader. So you work in it in your viewport, and then you bake it out to a shader, and then when you go to render, what you see in your viewport and what you see in your render are pretty similar. And what I like to do is, because I use Arnold for rendering, I tick on this bake emission and I save the emission as CE. And this basically means that I can use this look in Arnold. It changes it a little bit. It's not as close as Karma, but I much prefer the speed and the quality of Arnold. So that's what I've done here, is basically create the CE, and if I go to the shader, I think I have to come to the render here, explosion render. You can see I've got a material here, so I'm just reading in my explosion, I'm trailing this, and then I've got this explosion. If I jump into this net here, explosion, and I'm reading this in as CE, I'm just computing the length, and that goes into the emission, and the CE also goes into the emission color, and then just out to volume. So it is super basic, but it saves you so much time, and you get a look that's very similar to that pyro bake. So if we come back up here, so as for settings, I've got basically white smoke, the shadow is quite dark, density of 10. So if you come into bindings here, you can see the density is going into the color, and the temperature is going into the scatter, and it's being masked by the density. So we're basically multiplying the density with the temperature to get this like sort of crispy look. So if we come over here and you enable mask, if I enable this, we no longer get that sort of crispy look. But if you want a bigger looking explosion, you know, enable this. We're not using the fire, we're not using the secondary. It's basically just that. And here you can see I'm actually just deleting the scatter and temperature because I no longer need it. I now have just density and CE. These are the two things that I'm going to use for rendering. And if I want to visualize it again in my viewport, I can put down this volume visualization. And you can see under emission, I have density, and the field is CE, and under smoke, I have the density, and this is a value of 10, which is the same value I had here. So 10. Now you can see there's a bit of a difference. It does change a bit. But if you want to render this in Arnold, this is the way to go. And then I just save that out to disk, and this I can read in for rendering. The very last thing that I did is I'm reading in the debris source. So this is from our debris that we set up. So we're reading in this here. That comes in creating an attribute called speed based on the length of the velocity. And I'm then coloring this. So if I untick this here, so I just have this very first impact here. And I'm then deleting anything that isn't white. So we just got these points on the very first frame. And I'm feeding that into a pop simulation. And it's pretty simple. We just have a pop replicate. and some pop wind and a gravity. So super simple. And here we're reading in our collision, and here we're just saying that if the sparks are inside this volume, we're just going to remove them. So you can see these are basically just getting deleted. Next up, we're going to set a p-scale on this between 0.33 and 1.2, and this is just on random points. So this is just going to be randomly set a p-scale. We can take a look at that if we do this. Copy the points. Put down a sphere. And now you can take a look at the p-scale. So here we're going to be basically setting some length for our sparks. And you can see some of them are long and some of them aren't. And that's just because we're setting a velocity based on the time. So if I've just put down this, if I were to just use just the frames, so we look at, I've taken a time shift and I've -1, and then I've merged those together. So this was like a typical way of trailing something. And we're looking at where it is on this frame and then where it was on the previous frame, and then creating a line. And we just get something a bit uniform, but and also it's not going to match our shutter speed correctly. Whereas if we use our time and the velocity and we just add this to some points, then we're going to get more of a natural look. And that's what we get from this trail. Then I'm just putting down an add, and we're going to set add by ID. Here we're just going to give our points a color and merging it with another copy, because this one I did for the legs. So here's my debris source. We're reading that in from out debris from for sparks, so that comes from here. So we're reading that in, and this time I'm just using a bound to delete what I wanted manually. So I'm just going to template our character quickly. So you can see here I wanted, because these legs break apart, and I wanted some sparks to come from this area. So I've just put a bound there. I'm adding some curl noise to the velocity. So if we were to take a look at our velocities, let's come back to find the point. Let's undo this for now. Yeah. So here you can see our points just are flying out like this, but now with some curl noise, we get a much more chaotic and random velocity. And that is just coming from this curl noise. See if we were to disable this. It's just adding a little bit of overall direction, and this is the main one. And this is also coming in from our frame to the offset, so this is going to change on each frame. If you want to know more about sparks, you check out Hunter's course on Magic. There's a whole week dedicated to just sparks and being able to get, you know, the correct amount of motion blur on your particles. And when I say motion blur, it's actually calculated in SOPs. And the course is designed in a way where you would be able to look at a reference and be able to make any type of spark look that you would like. So again, I'm really just isolating these sparks to the legs here. I don't think this blast is doing anything, so I'm just going to undo that. Again, this is my little tool that I like. I originally used this for water simulations, so I could run flipbooks and reduce my number of points. So you can see here, I often use this on my pop sims, and I just looked at my results and I was like, it's got too many sparks. So I threw this down and then I was able to dial it in. So here's the original amount, and I just bring this down to reduce my number of points. And here I'm just putting on a switch. So I want the points to appear here. And then disappear, and then appear again, and then disappear. And I was just using a switch to manually do that. So here I've pretty much got a very similar pop sim, just some pop drag and gravity, pretty simple, and just cache that out to disk. So this is going to be for the legs. Same again, setting a P scale, setting a trail, adding those together, setting a color, and then merging that all together.
So the very last thing just to show is very simple. There was nothing really fancy with the shading or lighting in this setup, but my render node is in the out context here. And if you don't have Arnold and you want to render this with Karma, please check out our tutorials on rendering with Karma. We covered pretty much everything that you'll need to render the scene in our previous tutorials. So thanks again for watching, and don't forget to like, comment, and subscribe, and I will see you next time. Thanks. Bye.